Hi guys. Today I'm going to cover the introductions about pulse laser and also the power calculation. So first, let me introduce you what is pulse laser and how it is different from continuous wave laser. So the left hand here, it is the like a power profile of like a normal continuous wave laser. You can see that it's giving out the power constantly in time, and it has only one power, which is the average power over the time. But for pulse laser, it is similar like having like an on-off period of the light pulse. Like you will have a very short duration where the light is on or the power is being delivered, and there will be the part where like there's no power or it's similar to laser being off. So with this um pulse laser giving energy in like a package, so it can have a very high peak power here, but during here there's no power, so eventually the average power it's still very low, but it will give a very high peak power in this very short period of time. So how short or how long one duration of light being on or the pulse is called pulse duration or pulse length. Like for example, here is 25 nanoseconds, which means that here is 25 nanoseconds that the light is being on. And another parameter is the repetition rate, which tell how many light pulse there are per second. So the unit is in hertz, similar to frequency. And for this example, is have 30 kilohertz, which means in 1 second there are 30,000 pulse, and each pulse is 25 nanoseconds. And with this repetition rate, we can know how long the off period or how separate each pulse is from the. So here the time difference duration here will be equal to one over repetition rate, or it is simply similar to period, which means how long it takes for the next pulse to come. And in this example, it would be equal to 1 over 30 kilohertz, approximately to 33 millisecond, which means that these two poles are separate by 33 milliseconds. And the average power is what we can measure using the photo detector. But for the pulse length, we use the technique called technique or the machine called autocorrelator, which use the pulse to measure how long its own pulse is. Like similarly to interference in time. And for the repetition rate, it use oscilloscope to measure, which is the frequency or measure the periodicity of the pulse. And next is the calculation. With these parameters, we can calculate. The first is pulse energy, which tell how many energy it is per pulse. So it is calculated from the average power over the repetition rate. Okay. So from this example, would be 2.5 watt per 30 kilohertz. And since hertz is 1/second, so this will go up into watt second, which is equal to joules. And it is tell how many joule there is per one pulse. It's similar to we divided these area under the power and time graph with how many pulse there are. So it's like 30,000 pulse equal to 2.5 watt. And after we can get the pulse energy, then we can calculate the peak power, which is the energy that is confined in one pulse. So that energy but divided by the pulse width, which is usually pretty short. So from the pulse energy equal this. And divided by the pulse width. So this would be joule per second, and it's also equal to watt. So this would be so you can see here that it will give us like very high peak power comparing to average power. Watt or around 33 kilowatt comparing to the power average, which is only 2.5 watt. Which means that in that very short time, there's 33 watt that confine in that pulse. And the peak power will depends a little bit on the temporal pulse shape or the shape of the pulse in time. So there is two type, which is the red one here, which is the second hyperbolic shape. Another one is Gaussian shape in blue here. It's slightly different, and there will be another constant time to this peak power depending on the pulse shape. And this is the example from the result from autocorrelator. And to find the pulse width, we use the definition called full width Hammett, which means that we take the maximum and then we find the middle part, and then we measure the full width of that part. So the full width have maximum pulse width for this will be 1 picosecond. Okay, and that is overall pulse laser calculation. The important part here is that since the power is confined in very short time, it can give very high peak power, as you can see here, despite having like normal amount of average power. And that's how pulse laser is different from continuous wave laser. Okay, and that's it for today's videos about pulse laser calculation and introduction to pulse laser. Thank you for watching and see you guys in the next video.